Welcome to the next video in our Systems Devices 2 networking series, where we continue our journey into the transport layer. Okay, before we get started, let's have a look at what we did in the previous week. So we were looking at UDP, User Datagram Protocol, and I asked you to start to think about writing a program to transfer the image of Bob across the network between two machines. Perhaps the PC and the Raspberry Pi, but it could be on your home computer, so across the loopback network. So we haven't seen this one yet, but as always, it's coming in a future lecture and a future lab. On all PCs, you have the concept of a loopback interface. So an IP address that is assigned to a virtual network interface, a virtual NIC. 127.0.0.1, for example. So you have a huge range of virtual interfaces that you can use to communicate on the PC. So it doesn't actually go out onto the network, but these are virtual interfaces that you could use to test out your program. So one of the programs could transmit on 127.0.0.1 and one could receive on 127.0.0.2, for example. So in this week's practical session, you'll be actually writing this code. So do as it says there, spend a little bit of time thinking about those code fragments that I gave in the last lecture, seeing how you can put those together to implement your file transfer programs. In addition to that, I asked you to have a look at TCP, just a quick read around, look at that RFC, see what you thought. And what you should have instantly noticed is the documentation is a lot bigger because it's a lot more complex. And we'll be going through this one at a reasonable level, looking at all those main features of how TCP handles lost corrupted packets, retransmissions, congestion control, all the key features, but we're not necessarily going to go down into all the subtleties. So to some degree, we're going to skim across that, but you will get a good understanding of what's going on. We'll be looking at this in Wireshark as always, and seeing what happens on the actual network in these scenarios. Right, and as I probably bored you to death in the last lecture, we saw that UDP is an unreliable network, whereas I kept hinting that TCP was a reliable network. So what does this actually mean? What are the differences between UDP and TCP? And that's what we're going to look at in this week's lecture. Again, TCP, our transmission control protocol, was one of the founding member protocols of the internet. So it's been around a long time. It's a core protocol that basically defines the internet in many respects. I guess the key thing for me that differentiates TCP and UDP is that TCP is a connection-oriented protocol. So before you can communicate any data between your client and your server, between the two hosts that you want to create this communication link between, you have to set up the connection first. So you have to have some handshaking at the beginning to ensure that both hosts are ready to communicate and agree some basic parameters on how they'll communicate. Also, don't get confused that TCP is not a circuit switch. So in circuit switching, we saw in the first lecture, you created that communication link between the two phones in that example I gave there. So you created the circuit between the two phones that you want to communicate across. So although we're creating a communication channel between the two transport layers on the two different machines, this isn't a fixed link in the sense that the lower levels have reserved communication links for you for this communication channel. You're not performing circuit switching at those lower levels. Again, the same as UDP, we don't care how this communication link is formed at the lower levels below the transport layer. It's a logical connection. It's a point-to-point connection between two machines at that transport layer. So as I say, before you can communicate anything across a TCP connection, you have to create this channel, you have to synchronize the two machines, but once that communication channel is connected, it's typically a persistent connection. So you keep this communication stream open, and it's a bidirectional connection. So as soon as that connection is made between the two machines, so host A and host B, that means that A can send data to B and B can send data to A. It's a bidirectional link. And TCP supplies all the things that were missing from UDP. So as you transmit your packets between the two machines, if some packets take a different path and take more time to get to their destination, that is if packets are received out of order on the receiving machine, not a problem with TCP. TCP will handle that. It'll reorder them into the correct sequence before passing up to the application. Again, if any packets are dropped because there's errors, or if any packets don't get received, get lost on the internet, TCP will handle that for you for your application. It'll handle retransmissions. So it's a reliable connection. So the data being transmitted by your transmitting process is guaranteed to be received in the same order that it was transmitted by the receiving host, and any errors corrected before it is passed up to the application layer. And all of this happens transparently to you as an application programmer. It just magically happens. So to implement that functionality, we need one or two more fields within our headers to allow us to detect when things have gone wrong. And that's what you can see here. So this is the TCP header, and it varies in size depending on what you're doing. But at a minimum, it's 20 bytes long. And as it says there, it can be an extra 40. So it can be anything from 20 to 60 bytes of stuff. So you've got core fields and some optional fields, and then obviously the data you want to transmit. So exactly the same as UDP, you again have ports, so you have your source and destination ports. Now we have some sequence numbers and acknowledgement numbers. These are used to control the flow of data and also used to detect if data has gone missing. So each packet you send is given a unique number, and if there's any break in the sequence of these numbers, you know something's gone missing. Again, we have a checksum to allow us to detect if things have got corrupted, and we have some flags and other fields here. Because the TCP header can be variable, obviously the receiving host doesn't know how big it should be, so we specify the size, the length of the header in this field here. We're not going to cover the urgent pointer, urgent flag here in any detail because it's not overly used, shall we say, not commonly used. We're going to focus our attention on these flags here because these are the ones that are used. So we have our acknowledgement flag, our push flag, our reset, our sync, and our finish. And these are used to indicate the state of our TCP communication channel and also the phases it goes through making that connection. In addition to that, we have our receive window. We'll look at that one towards the end. And that is used in flow controls. Allows the transmitter to throttle its communication speed if the receiving host can't keep up, for example. So we'll have a look at all of these in detail as we go through. Rightio, so in the lecture review sessions, to give this some context, we'll be doing some demos. So we'll look at how we can create a simple server on our Raspberry Pi that will convert lowercase strings into uppercase strings. So you have a server on a remote machine, and if you send it data, whatever data you send, it will convert that ASCII data from a lowercase to an uppercase representation. So in this example, we have a Python client accessing this server, so it will send the string hello world in lowercase, it will send it to the Pi, and it will receive the same string, but it'll be capitalized, so it'll be hello world, but in uppercase characters. So we'll have a look at how we can implement this communication link using TCP, and there's different ways of doing it, as it's sort of showing you here. So single, multiple, and continuous modes, because a key difference between UDP and TCP is that communication channel. So once you've created it, it's a stream. Whereas in UDP, you're transmitting individual packets of stuff. In TCP, you create a stream and then you can send single or multiple or continuous amounts of data across that stream. A different way of thinking about how you organize and send your data. It's either packets or streams. Hopefully, fingers crossed, when we've looked at these Python examples, that difference will be made clear. However, before we can communicate any data, we need to create that communication channel, and that's what we're doing here. So when we open up our socket and connect to our TCP port and IP address, we'll perform a three-way handshake, and that's what we're going to look at next. So here in this example here again, we've got a sequence diagram, we've got the client and the server, time is going down. So the client will send a connection request, it will send a SYN packet, that is the synchronization flag. So it'll set the SYN flag in our TCP header. Within this packet, I've just highlighted the main core stuff. So it'll have a destination port and a source port, exactly the same as UDP. The destination port is fixed on the server, so the server is always listening, in this case to port 8000, and the source port obviously from your client will be an ethereal port from the pool of ports that can be used in these connections. However, unlike UDP, we have now a sequence and an acknowledgement number, and these numbers are used to keep track of the packets that are sent across the network. Initially, the sequence number coming from the client is just a random 32-bit number. And in general, this will be incremented by the number of data bytes contained within your TCP segment. So how many bytes of message have you transmitted? The exception to this rule are packets where you've got the SYN/SYNACT flags set, and in which case they'll be incremented by 1. So here the length value is the length of our data. It's not the length of the TCP header. That obviously, as we saw previously, that will be at least 20 bytes. This is just to show that there's no actual data sent in this synchronization request. The information that we need to pass to the server is contained solely within the header. So our server will receive that SYN request. As this is a connection-based protocol, it will need to reserve space for buffers and variables to show the status of this connection. So some memory will need to be reserved on the server for each connection. The server then will respond back to the client with a SYN-ACK packet, again on that client, to allow it to work out who this packet has to go to, we again use our assigned port. So we have a destination port, which will obviously be the same as your initial source port. So that's how it knows that this packet is for him. Again, this packet will be allocated a sequence number, and again that will be initialized to a random 32-bit value. But you can see that the acknowledgement number is acknowledging the sequence number from the previous packet. So previously it was 0 because at the start of the communication there was no acknowledgement to be made. This is a fresh new communication. But here, this packet here is telling the client it has received this packet. So this sequence number here is your starting count value. And because it's a SYN packet, the server is saying, okay, I'm going to take as a length of 1. I know it's got no data, but in this scenario, it does take it as a length of 1. And so it's saying, I've received up to 5A, 07, 6E, 12. By returning back to the client, the value 5A076E 13, one more. So it's saying, this is the number I'm expecting next. So I've received everything up to, but not including this sequence number. So when the client receives that, it knows that the server has received this packet because it's acknowledged its reception. Again, the client receives this packet, goes, right, I now know the server is ready to start this communication process. It's allocated its various state variables and buffers. I will now do the same. I will allocate some space here for my side of the connection, and I will inform now the server that everything's good to go with an acknowledged packet. And again, we will be using the same source and destination addresses. Now the sequence number, you can see here, has gone up to 1. It's the next packet that we'll be transmitting. This packet here also acknowledges to the server it has received its packet. It has received its SYN request by incrementing its sequence number by 1. So you can see that's gone up by 1. And after that packet is received, the server also knows that both sides of the communication, both sides of this logical link are good to go. And now we can start to transfer data in either direction. Remember, a TCP connection is a bidirectional connection. So after these 3 steps, your connection has been formed. You have your TCP connection. Okay, so our connection has now been established. And again, remember, to illustrate this communication process, we're using that Python program where we have a Python program running on our server. So it's listening on port 8000 for text strings to come in. It will receive those and then capitalize them and send them back to the client. So we have our client here and he wants to send the string hello world. So again, it'll create that as a packet. Now this string obviously is very short, so it'll fit within one packet. Remember, our MTU is typically around about 1,500 bytes, so we're well within that. So that will be transmitted as one packet to the server. So again, we have our source and destination ports, which define the connection, who we're connecting to. Remember, after the three-way handshake, our sequence number on the client was the value ending 13, not to say that big long hexadecimal value. And the acknowledgement value, i.e. the packets that the client has acknowledged from the server, will remain at the same value. So this is telling the server, this is what I have received from you. This is sequence number of the next packet I'm expecting from you. So this will just remain static until it does receive more data from the server. Okay, so again, the value 11 is the number of bytes within the message. So each character is a byte, so it's 11 bytes long. This is not anything to do with the length field in the TCP header. So this packet will be sent to the server. If this data should be sent up to the application layer, then the push flag will be set. So the push flag doesn't indicate that this packet contains data. It indicates to the server that the data it has received up to this point should be pushed up to the application layer. So you can send data from the client to the server and the push flag will not be set. As an example, think if you're sending a book, you want to send lots of data. That data will be received and buffered on the server, but you only want to send that data up to the application layer when you've sent a chapter or something, a reasonable chunk of data. And that's when the push flag will be set. So don't think that all data packets have to have the push flag set. That's not true. It's that signal to use the data to the server. Okay, so in this case here, it will be set because our string hello world does fit within one packet. Okay then, so our server will receive that packet. It'll then inform the client that it has received that packet by sending an ACK packet, an acknowledgement packet. In general, this packet has no data. There are some exceptions around that one, but we're going to take it in this case here. This is a distinct ACK packet that has no data within it. Its sole purpose is to acknowledge to the client that the server has received this data. So the sequence number here will be exactly the same as the acknowledgement number in the client's packet. Remember, this acknowledgement number, this is the next sequence number the client is expecting from the server. So obviously that's why it's in that one there. The acknowledgement number obviously will be whatever this sequence number is plus 11. And obviously that's in hexadecimal. So if you do that calculation, 13 plus 11, decimal that is, will give you 1D. So the server is telling the client it's received up to, but not including this sequence number. So we received everything up to 5A076E1D, and the next number it's expecting is E. So it's always one more, which sometimes catches you out. So the client can now delete that packet from its transmit buffer. It doesn't need to retransmit it. It's been received, delete. Okay, so our server receives that string, hello world, and obviously the purpose of our server running on here is to convert that string into capitals, so it'll do that, process that data, and then transmit that packet back to the client so he can use this new updated data. So again, our destination source ports remain the same because these define the connection. Again, the length field here is the length of the data. That hasn't changed, just gone to capital letters. The acknowledgement number will remain the same. Obviously, this is the sequence number that the server is acknowledging to the client that it has received up to. So it's received everything up to ending 1D, as we discussed previously. You can also see, though, that the sequence number here of the server's packet, it also hasn't changed. It's exactly the same as the sequence number of the acknowledgement packet. And that's because acknowledgement packets do not increase the sequence number. So within the data transfer period, your sequence number is only updated if you're sending data. So here, no data, so it doesn't get incremented. Think of your sequence number as a byte count. So think of your sequence number as how many bytes of the message have I transmitted. It's just a counter. Okay, so our sequence number will start at our last count value. So start ending 5D. And again, that will be incremented by 11 because that's the size of our string. So that'll be 5D, E, F, then 60, 1, 2, 3, 4, 5, 6, 7. So you're using the sequence numbers starting with 5D all the way through to 67. And those correspond to that string. And again, same as our previous packet, this short string will fit within one packet, well within the MTU. So the push flag will be set, telling the client to push this received data up to the application layer. So that is transmitted to the client. The client will receive that data. The client will then send back to the server an acknowledgement to tell it that it can delete that string hello world from its transmit buffer because it's been received on the client. So here we have our acknowledgement packet. Obviously the port numbers remain the same as always. So this packet contains no data, so the data field length is 0. The sequence number will be ending 1E because we've used the previous sequence numbers from E13 to E1D when we last transmitted the data. So on the client, its current sequence number is ending 1E. So that's what will be in the sequence number field. The acknowledgement number, as we were discussing, will acknowledge the reception of this data packet. So this data packet, the sequence numbers for the server will be ending with 25D up to 267 off of this data string. So the client will acknowledge that it received all of that data and say, right, the next sequence number I'm expecting from you is ending 268. The server then will receive that packet, and then it knows it's safe to remove this text string from the transmit buffer because it's been received on the client. It's no longer required for a retransmission. One point to highlight here within this communicating process, you'll see that the ACK flag is always set in these packets. When you see the ACK flag being set, that doesn't mean that it is explicitly acknowledging new data. Rather, it's showing you that the acknowledgement value within the packet is valid. So you can see here we've got push ACK. So this ACK here isn't saying, oh, something's changed, something's new, something has to be acknowledged. It's just saying that this value here is valid. So not all packets containing ACK flags are acknowledgements. I feel like digging a hole here. But you'll see that when we go through some Wireshark traces, you'll see lots of ACKs being set, but do differentiate between packets that are acknowledging stuff, and these will be 0 length packets typically, and packets where the ACK flag is set and you're actually sending data to the server. And don't worry, we'll be going through lots of examples in the labs, and hopefully after a while it will all start to settle down. But I do 100% agree that the concept of a sequence number and a acknowledgement number is simple. It's just a counter. But the implementation, because you've got sequence and acknowledgement numbers on the client side and you've got sequence and acknowledgement numbers on the server side, and obviously they're different, it gets very confusing very quickly. So with a little bit of practice and doing it nice and slowly, writing stuff down, fingers crossed, touch wood, it all makes sense in the lab. So trust me on that one. We'll be going through this in a lot more detail in the lab. Okay, then at some point we'll come to the end of our communication process. So we will have sent all the data we want to our server. So again, remember TCP is a stream. So you can keep this connection open and you can send a single piece of data, multiple pieces of data, or a continuous stream of data to the server. It's not like UDP where you just send one packet of stuff to the server and then that's returned. This is a continuous bidirectional stream of data. But at some point you will want to close this connection. So to signal to the server that the client has finished, the client will send a fin packet, a finish packet. So it will set the fin flag within the TCP header. Again, there's no data associated with this packet, so the data length will be 0. The sequence number will be the same value as from the previous slide because we haven't sent any data yet. And the acknowledgement number won't change because we haven't received any new data from the server. So the acknowledgement number here will also be the same as last time. So this is sent to the server. The server then will acknowledge the reception of this fin packet. So therefore, just the same as a SYN packet, fin packets have a notional length of 1, even though they don't contain any data. So you can see here, the acknowledgement number has gone up by 1 to signal to the client that the fin packet has been received. And as always, the sequence number is the previous acknowledgement number, as that's the sequence number that the client is expecting to receive next. Okay, so at this point here, the client knows that the server has received its request to close this connection, but it won't close the connection. It'll stay here waiting for the server to send a fin flag to say it is closing its end. So here we've requested that our end of the TCP link should be closed, but this end of the TCP link is at the moment still open. So that at some point the server will send a fin packet to the client. So as always, the same destination and source ports. So we're sending this packet to the client, so we'll be using the current sequence number on the server. So this again, ending 268, hasn't changed yet because we haven't sent any data. And again, the acknowledgement number will remain the same. The client will receive this packet and it will send back an acknowledgement to show that it has received it. So again, fin packets have a size of 1. So you can see the sequence number here has been incremented to 1 to tell the server that you have received its request to close this connection as well. So when we get to the end of the sequence diagram, both ends are closed, the connection is finished. Rightio, so hopefully from that set of sequence diagrams, we can now see that TCP has an explicit initialization sequence, so that three-way handshake, and positive acknowledgements for each transfer. And obviously that's how it detects if the host you're trying to transmit to is there and ready to receive, and if there's any packets that go missing. But that comes at a cost. So if we looked at our kind of hello world example, to send that one data string with UDP, one segment, just transmit it and away you go, fire and forget. With TCP, you're looking at 9 segments, and obviously there's a lot more communication going on there. So if we go back and look at our sequence diagrams, so for every TCP connection, you need 3 packets to set up that link. That's your three-way handshake. Then for each packet you communicate, there'll be in effect 2 packets. You transmit the packet you want to transmit, and you have to wait for the acknowledgement to confirm that it has been received. So we're up to 5. And then we want to finish our communication. You've got 4 packets worth of shutdown. So again, some finax going on. So there be your 9 packets. You can argue this one. Obviously, with TCP, it's a stream. So you can consider, obviously, the initial setup, the three-way handshake, and the final close down as exceptions. So you do that once and you create that channel. So in effect, you're only kind of doubling your network usage, if that makes sense. If you ignore the setup and the shutdown, then you've just got that additional ACK coming back that you need to process. And again, there's ways of minimizing the number of ACKs that you do need. But even still, UDP is obviously a lot smaller. You just send that packet out. You don't care if anyone's listening. You don't need to initialize that connection. You don't need to close down that connection. You don't need to confirm that that packet is being received. You just fire that one packet out and job's good. And that's the advantage of UDP. It's very simple, very quick, but obviously unreliable. So as I say, that initial setup and then closing, you don't want to be doing that all the time with a TCP connection because that comes at a cost. But that adds complexity as well to actually how you communicate between the two devices. With UDP, there's a natural delimiter. You naturally break down your communication process into a number of separate packets. So you want to send 10 characters to the receiving device, one packet, and that is the container for that part of the communication. But with TCP, it's a persistent stream. It's a persistent bidirectional stream. So you now need to add delimiters within that stream. You need to some way of telling the receiving device that the chunk of data has been sent. And that does add complexities. And we'll see that when we look at our simple Python example. So that example where we're capitalizing the strings. So sending one string, multiple strings, or a continuous stream of strings. Just some points to note there. Reliability is implemented through positive acknowledgements and timers. So we have a look at those ones next. So sometimes packets can go missing, you won't get the acknowledgement back or you won't get a data packet. So we need to detect those situations and we do that through timers. So we have a timeout in the TCP protocol. I guess sometimes we forget at this point here the overhead associated with a three-way handshake. Typically when we look at examples like this in the lab, we're creating these connections between the Raspberry Pis on a local network. So the delay is very minimal. That's the client and server may not be on the same network. So if you're contacting a web server somewhere in the world, there'll be a significant overhead for each HTML object you want to transfer because the round time trip is going to be significant now. It's not going to be fractions of a millisecond to make those communications. So you can see that through the development of HTTP. So originally they were non-persistent links. So for each HTML object you want to transfer, you'd open and then close down a TCP connection. And obviously that's a minimum of 9 packets as we saw previously. Now connections typically are persistent. So you'll send multiple objects over the same connection. We start to introduce the idea of HTTP streams, but that's another topic to look at later. So I say we'll look at those, how we handle our TCP connections for single, multiple and continuous usage in the lecture review sessions. We'll look at that one running on our Raspberry Pi systems and go through that code. Rightio, so taking those examples as inspiration, what I would like you to do is start to think about how you'd re-implement our Bob file transfer program. So how would you re-implement the UDP implementation to use TCP? So one way of doing it is to basically treat the TCP connection as if it was UDP. But that is not a very efficient way of doing it. You'll be opening and closing connections repeatedly, and that is just wasting time. That is not the best solution in terms of minimizing the number of packets you need to send across your network. So do have a stop and think about this one. Do have a think about how you could implement an efficient implementation of our Bob transfer programs, our transmitting and receiving programs using TCP. And like the UDP programming task, we have a separate practical session allocated where you can sit down and think about implementing this solution. Because again, sometimes it's not until you sit down and try and do something that you realize you don't actually really understand the concept that you're trying to use. So this programming task, like the UDP programming task, is a good chance to make sure you do understand how TCP operates. There's a few twists and turns in the story. Okay, time for a quick quiz to see if you understood what we just looked at. So in this diagram, we have a series of packets that are being transmitted from the client to the server and a series of acknowledgements coming from the server to the client. So here we have segment 0, 1 and 2 and their associated acknowledge packets. So your task here is to fill in the missing blanks. So in the first scenario, these packets will be received in order. So the receiving host, the server, will receive segment 0, then 1, then 2. So what would be the associated ACK packets coming back? But what if, for some reason, segment 1 got delayed? It took a longer path, because remember the path isn't fixed with packet switch network. It may vary. Obviously each packet goes through a router. For some reason, to send that particular segment via a different path. So it still gets to the same place, but may be slightly delayed. So the server will receive them out of order. It will receive them in the order 0, 2 and 1. So what would the ACK packets look like in that scenario? As always, we'll look at that answer in the lecture review session. Okay, so What we've looked at so far are the typical use cases. So that was the easy bit. Now we need to consider what happens when things go wrong. So in that quick quiz, we had an example of that one. When the packets are received out of order, how do we handle that in the TCP protocol? So going back to our IP over AC example, so when we release our pigeons, when we send our TCP segments out into the world via our carrier pigeons, obviously the time of flight for each packet, for each segment may vary. Some pigeons may take longer than others to get to where they're going to. Equally, when they receive, what order they will be received in determines what order they'll be queued and what order you'll process them. So it's very easy for packets to be received out of order. And if we went back and looked at our UDP program that transferred the image of Bob across the network, you can imagine if those packets were received out of order, strange things would happen when you try to regenerate the image of Bob. We need to be able to handle that in some way. You need a mechanism to handle that in TCP such that you can regenerate the sequence of packets and pass them up to the application layer in exactly the same order as they were transmitted. And also, as you can imagine, that may be our best case scenario. We receive all the packets but not quite in the right order. Obviously the worst case is if we start to lose packets. So if packets aren't received at all, we need some way of triggering a retransmission. So to help us think about that, I've written out some pseudocode because everything's easier to understand in pseudocode. Well, we'll try our best here. So this explains the sequence of events that can occur when you're transmitting packets, describing what happens in the transmitting host. So what happens as we transmit data onto the network? What do we need to start to think about? And if you've looked at the TCP documentation, you'll straight away identify that this is a very simplified view of things. It's actually a lot more complex. But hopefully this pseudocode will explain the basics. So in the pseudocode, we've got some variables. So we've got the next sequence number. So initially, that's just a random 32-bit value. Initially, the previous sequence number is also updated to that value. And we have a zero-length segment. So we have no data to transmit. Then you can see here we have an infinite while loop. And within that while loop, we have 3 events. So a message can come down from the application layer. That needs to be transmitted. We could have a timeout. So previously we have transmitted some data, but we haven't received an acknowledgement within a reasonable amount of time. So we want to retransmit our data. And the third event that we can have is that we do receive an acknowledgement. So at this point here, we know we can remove some of our data from our TX buffer. So we don't need to keep a copy of it anymore because we've got an explicit positive acknowledgement from the receiving device that that data has been received correctly. So let's have a look at these each in turn. So we receive a message from the application layer, so we need to create a segment. So we create a segment with the data that has been passed to us and we assign it the current sequence number. Then we look at our timer. So think of the timer as being associated with the oldest unacknowledged packets. So if there's a timer running, that's fine. But if there's not a timer running, then we need to start our timer. Then we pass down to the network layer our segment that we want to transmit. And then we give up control of that one. Obviously, then the network layer will transmit that for us. And finally, we update our sequence number. So our next sequence number is just the current sequence number plus how many bytes we transmitted. So our message will be a certain number of bytes. So if it's 10 bytes long, then the next sequence number will just be whatever the old one was plus 10. So once we've transmitted that packet onto the network, 2 things can happen. We can either receive an acknowledgement or a timeout will occur. So if our timer generates a timeout, that is, we've waited the specified amount of time and we haven't received an acknowledgement, then we'll retransmit the oldest segment that has not been acknowledged. So again, we'll pass down to the network layer the segment that hasn't been acknowledged and has the smallest sequence number, because obviously as we transmit packets, the sequence number will be incremented. It will get bigger each time we transmit a packet. And we'll restart our timer. So again, we retransmit that packet and we start the timeout and again wait for another timeout or a acknowledgement. So this time let's assume that we do get an acknowledgement back. So that packet will contain an acknowledgement number, and that number can be used by the transmitting host to determine how many bytes the receiving host has received. There's a couple of different scenarios that can happen here. So if that acknowledgement number is greater than the previous sequence number, then we know that the remote host, the receiving host, has successfully received some data. So remember, the acknowledgement number is based on the transmitted sequence number plus the amount of data the receiving host has received. So the number it will return should be greater than our previous sequence number. So in the previous example, if we sent 10 bytes, this number here will have acknowledged that it's received bytes 0 to 9, and the next sequence number it's expecting is byte 10. So our transmitting host can now remove from its transmit buffer, from the list of segments it has transmitted, everything up to the acknowledged sequence number. Then it updates the previous sequence number to the received acknowledgement number, because that indicates how many bytes the receiving machine has received. Again, if there are unacknowledged packets still out there that haven't been positively acknowledged by the receiving machine, we restart our timer and wait for those to occur. And again, a timeout can occur, or we receive those acknowledgement packets. Now, there are a few edge cases around this scenario, examples where you receive an acknowledgement packet and the acknowledgement number does not change. Or you can receive an acknowledgement packet that acknowledges multiple segments, cumulative acknowledgements. And we'll see those examples as we go through here. But the basic idea is that we'll have timeouts to detect when things get lost. If I don't receive an acknowledgement, I can retransmit after a specified amount of time. And I have sequence and acknowledgement numbers that allow me to keep track of what has been transmitted and what has been received. So it's the combination of sequence numbers and timeouts that give us our reliability. But then this raises the question, how long should I wait for my packets to be received? What is a reasonable amount of time? And you can see that from lab 1. So if you were communicating with a machine in the building, then your timeout will be in the order of a few milliseconds. But if you're communicating to a machine in America, then you might be looking at 60 or 70 milliseconds. So obviously you don't want to set your timeout value too high, otherwise you're just waiting for things that never will be received. But equally, you don't want to set it too small, because you'll be generating timeouts all the time and retransmitting data when you don't need to, because you just haven't waited long enough for that acknowledgement to come back. So the choice of your timeout value is critical. Initially, however, the transmitting machine's got no idea how long it will take. All it knows about is it'll be transmitting to a particular IP address, and it does not know where in the world that IP address is located. Therefore, for each communication link, we need to have some equation that works out what is the best timeout value. So not too small that we keep triggering retransmissions, and not too long that we're waiting for stuff that never will arrive. So initially, we set our timeout value to be 1 second, as normally that's more than enough time to communicate anywhere in the world. From the ping examples we did in lab 1, you saw Australia was in a couple of hundred milliseconds. So waiting 1,000 milliseconds, it should have got there. I've got an acknowledgement back within 1 second. However, again, remember that this delay is not just your propagation delay, it's not just your communication delay, it's also dependent on the amount of traffic on the network, your queuing delays, your processing delays, how quickly the machine can respond to you. So initially our timeout is set to 1 second, and then we use this equation to work out how that value should be adjusted. So we can work out the round trip time by timing the time between the transmission and the reception of a ACK. So that'll give us our current RTT, and then just using a weighted average filter, we can generate a value for the estimated RTT. So we just don't update it straight away with the current value, because there may be some fast packets, some slow packets. So we add on to our estimated value a percentage. In addition to that, the timeout is based on how the RTT is varying, so the deviation in the round trip time. So again, it's another weighted average filter. So the deviation is just the difference between the current and the estimated value. So how does it vary? So we're just getting the absolute value for here. And again, after we've received a few values, we can start to generate values for the deviation in RTT. So over time, for each communication link, we can work out what the timeout should be, because we'll be monitoring the RTT values. And as I said, we're looking for that Goldilocks value. We're looking for one that's not too hot and one that's not too cold. Finally, as it says there, if it doesn't receive an acknowledgement from the host you're trying to communicate to, that timeout value will be doubled. So initially it's 1 second. If it doesn't receive an ACK, it will retransmit and then set the timeout to be 2, and then 4, then 8, then 16. And it goes on for quite a while. So sometimes when you're doing a network communication and it seems to stall, that's probably what's going on, especially if it's at the start of the communication process. So sometimes the client is quite dogged and it won't give up trying to communicate with the server. So it'll wait a significant amount of time. So as you can imagine, with that exponential increase in timeouts, it can result in a significant timeout value before the client finally gives up. As always, we'll work through an example in the lecture review sessions. We'll do a demo here. So one way of generating missing acknowledgements is to add a network delay. So using the traffic control command, so you can see here we can add a 5-second delay on a communication link, which obviously will delay the reception of our ACK packets. So it's expecting an ACK packet after a second, but that packet won't be received until after a 5-second delay in this case here. And that will trigger a series of retransmissions and various acknowledgements. So you can see here we've got some error messages coming up in our Wireshark trace. And we'll draw the sequence diagram of this one in the lecture review session. And fingers crossed, touch wood, I won't make any mistakes, but what we can see here is the interaction between the client and the server, the transmitting and receiving machines, and we can go through in the lecture review session seeing how these timeouts are calculated and when they'll occur and what that will trigger in terms of retransmissions on the transmitting machine. So we'll break down this packet trace you see here into a sequence diagram. And that's where we guess. Quite confusing, but fingers crossed, touch wood, we can work through this in the lecture review session and it'll all make sense. Right, yeah, I think this lecture's getting a bit on the long side, so I think I'm going to divide this into 2 chunks. So I think that's where I'll end this particular chunk, and I will catch you next time in the next video.